Swayam Prabha. Digital India. Educated India.
This maritime engineering, as you see, is a very special program which has got multidisciplinary input from mechanical, civil, structural, aerospace, naval architecture, chemical engineering, electrical, electronics, applied mechanics. It's a multidisciplinary program. You will find this program is completely different, dedicated to industrial training and thorough capacity building on the new trade of maritime sector. It's a grooming economy which will give you a lot of job opportunities and research frontiers as far as India is growing. And the Blue Corridor effect, which is planned by the Government of India, is one of the important mission which requires maritime engineering growth to happen in the country. So this program caters to expected that capacity building in this program.
Friends, this is part of a material science engineering laboratory which becomes one of the teaching aid for the maritime engineering program. So when you talk about materials innovation in maritime industry, though concrete and steel have been conventional candidates of choice for engineers, for example, we have titanium vessels, high-speed craft boats made of fiberglass. These are all advanced materials which actually do not come across conventional standard design code of practices. We conduct box furnace test, tube furnace test, vacuum arc melting, induction melting, vacuum induction melting, vacuum sealing unit, which are all present in this laboratory is a small segment of material science laboratory. Friends, a typical furnace where the operating temperature for testing specimen can go as high as 12 degrees Celsius. Generally at room temperatures and ambient condition, the mechanical properties will not alter much. As you see in the course lectures, you will notice that strength of the material get degraded when the temperature rises beyond 600. Therefore, when you talk about fire resistant design, you must also choose an alloying element such a manner that the strength doesn't degrade beyond 600 degrees Celsius at all. Welcome to the ambience of IIT Gandhinagar lecture theatre. This is one of the interesting classrooms where the maritime engineering classes will be conducted. We have got state-of-the-art projection facility and good audio-visual recording systems. Once the lecture is over, you see the system here. We can generate the PDF files of the lecture directly and you can email the PDF files directly to your email IDs. So it's a state-of-the-art facility we have in IIT Gandhinagar where the lectures are lifetime recorded and shared with the students immediately. This is the IIT Gandhinagar library. This has got all collections of books which are referred as the standard textbooks and references for the course and the program. It also has lot of online editions of design code of practices and reference materials and e-collections of various video lectures of international courses and programs related to maritime engineering. We will be taking you around to the advanced material manufacturing units. So you will have state-of-the-art facilities available at IIT Gandhinagar. So welcome to the program to join MTech and PhD at IIT Gandhinagar Maritime Engineering. So please try to enjoy and take the advantage of this to the maximum. Welcome to the program and welcome to IIT Gandhinagar. Friends, welcome to the 6th lecture on the SwayamPrabha course titled Maritime Structures, offered by Department of Maritime Engineering at IIT Gandhinagar. In the last lectures, we will start discussing about the types of maritime structures, paying more attention towards the conventional offshore structures meant for oil and gas exploration. We realized that as the depth of exploration goes deeper, the geometric form of these types of structures significantly vary in the substructural system. However, you must have noticed that the superstructure of the system comprising electromechanical equipments, drilling derrick, living quarters, etc. are all almost similar in all types of these structures. After understanding different types of maritime structures used for oil and gas exploration, we realized that the structural action of these types of structures become very important to design them in order to resist the loads acting on these structures. So, in the last set of lectures, we tried to explain the structural action offered by various geometric forms of fixed type structures and compliant type structures. We understood that both rigidity and flexibility are not good friends for alleviating the environmental loads acting on maritime structures. Then came into picture the new generation platforms, which is focused on this lecture. So, friends, welcome to lecture 6, new generation platforms. In this lecture, we will talk about one of those platforms, Triceratops. The word tri immediately resemble three-legged system. Historically, Triceratops are one generation of dinosaurs which has one long leg and two shorter legs. So, the conceived model of this biospecies was recommended and proposed in 1995 in one of the offshore engineering conferences in USA. Beyond that, no significant work was conceptually developed in this idea. At IIT Madras and now at IIT Gandhinagar, we are exploring the high possibilities of making this idea into reality. So, we will discuss this kind of a platform which is a thought-provoking presentation for people who are in research as well as for practicing professionals in maritime industry. Triceratops is one of the most innovative structural geometric forms which are completely novel and in place for the past 10 years on paper. Please understand that these structures are still in the conceptual development and they are not yet been commissioned in any deep waters. So, let us wind back and slightly see how a compliant structure used to be there for oil and gas exploration to realize the innovation of the Triceratops in comparison to the compliant system. Compliant platforms, of course, we agree they are recent development. They have been most successful for deep waters, and approximately deep waters refers to 1000-meter water depth. We know water depth alone does not qualify this adjective of deep water. It depends on hydrodynamic characteristics which we will discuss later in this course. However, as a thumb rule, we really classified waters as shallow, intermediate, deep and ultra deep waters by simply water depth as an index number. So, deep waters were comfortably useful for deploying compliant platforms. One classical example which you could recollect is tension leg platform, which is one of the most successful compliant platforms so far commissioned in deep sea. We already said that compliant platforms are designed to withdraw and to withstand critical and very critical sea states. We will talk about sea states in general, the classification and the nomenclature based upon the wave height and the wave period later in one of the lectures on hydrodynamics. For the time being, let us realize that sea state helps you to qualify the conditions at which the wave and wind load are acting on a given system. We know compliant offshore structures are segment and subset of maritime structures which are used essentially for oil and gas exploration and production. We already realized that this compliancy word refers to flexibility. More flexible systems or compliant platforms which actually alleviate and encounter the environmental loads not by strength alone but by the geometric form inducing large displacements. Classical examples, as we discussed in the last lectures, are tension-like platforms, tension buoyant-like towers, and now Triceratops. Before we understand the importance of compliancy, let us try to discuss the important motion characteristics of compliant platforms. One may ask a question, why do we have to understand the motion characteristics of compliant platforms? Friends, it is important to note that these platforms resist loads by large displacements, which is a rigid body motion. In that case, let us try to understand what are these classical degrees of freedom these platforms exhibit. We will take a point in space. We will mark 3 axes, 1, 2 and 3. We will mark this horizontal axis as x axis, we will mark this as y axis, and of course this as z axis or z axis. Now, the body, which is a ball, let us say, has a freedom to roll along x axis. We call this displacement as surge, which is displacement along x. The point mass can also move along y direction. We call this motion as sway, which is displacement along y direction. Now, the ball has a freedom to move along z axis. We call this as heave, which is displacement along z axis. Friends, nevertheless, you can also have negative displacements along these axes. Okay? So, surge, sway and heave are 3 displacement degrees of freedom along x, y and z axis. Let me write it here. Along x, y and z axis, we have surge, sway and heave. I can also have rotation about this axis. I have to mark the direction of rotation of this. So, what you do? You hold your thumb towards the positive direction of this axis. The remaining 4 fingers, when you fold, will give you the direction of this rotation. Try to do this. You put your thumb towards x axis, the rest 4 fingers of right hand will get folded in specific form. That gives me the direction of this motion. So, now I say rotation about x is roll, I can say theta x. Similarly, rotation about y is pitch, which I can say theta y, and rotation about z is yaw, which I say theta z. Thetas are rotations about x, y and z. So, let me write it here. Again 3 axes, we say about x, y and z. We respectively write them as roll, pitch and yaw. Okay. So, now the body in space has got 6 degrees of freedom, 3 displacements and 3 rotations. Having understood this, let us now look at the planes. Let us talk about xy plane. So, if you look at this figure, xy plane is an horizontal plane, correct? It is an horizontal plane. XY plane is an horizontal plane. So, the displacements on this plane can be referred as, the motion on this plane can be surge, sway. These are the 2 displacements measured on this plane. Now, you have one more plane, which is the vertical plane, which is either zy plane Okay, it's a vertical plane. Now this is an horizontal plane. Now I have a vertical plane. The displacements which are seen on this plane is heave. Okay, these are the displacements. Surge, sway and heave are the displacements, is it not? Out of these, two of them are on horizontal plane, one is along the vertical plane. Similarly, I can also write this for rotations. Let us say about x, which is roll, the trajectory of this will be seen on the vertical plane, the projection. Okay, if you see from here, the rotation about x axis will be projected on this plane. Am I right? Similarly, about y axis, which is pitch, the trajectory of this will be seen again on the vertical plane. About z axis, which is yaw, the trajectory of this will be seen on the horizontal plane. Am I right? See, this trajectory will be seen on this plane. So, interestingly friends, out of 3 displacements, 2 of them are on horizontal plane, 1 on vertical plane. Out of 3 rotations, 2 of them are on vertical plane and 1 on horizontal plane. So, there is a cross, okay, there is a cross happening, right. So, therefore, if I imagine a system which is floating in nature, floating will happen about the horizontal plane. I cannot allow the body to float in the vertical plane. Therefore, the floating will happen along surge, along sway and along yaw. These are the degrees about which the body will easily float. Along surge means along x axis, along y axis, about z axis. Okay. For example, if I have a vessel, if I mark the axis, if I say this is x axis, if I say this is y axis, z axis, so the vessel can freely move along x, along y, and the vessel can freely rotate about z. Okay. So, it means the vessel is free floating in surge, in sway and yaw. So, these are called flexible degrees. Now, let us look at the other 3 motions. Let us talk about roll, which is about x axis, talk about pitch, which is about y axis, talk about heave, which is along z axis. Okay. These 2 are rotations, this is translation or displacement. Remember, if you look at this slide, translation along heave is seen in vertical plane, roll and pitch are seen in vertical plane. See here, roll, pitch and heave are all will be seen in vertical plane. Can you say that? I repeat again. Look at this slide. We said that heave, roll and pitch are seen on vertical plane. So, I am writing it here. All these 3 will be seen in vertical plane. So, in the vertical plane, these motions should be minimum. So, I should say in the vertical plane, the system should remain rigid. In the horizontal plane, the system should remain flexible. So, I am summarizing here, in horizontal plane, the system will remain flexible. In vertical plane, the system will remain rigid. Okay. So, now such a combination in maritime structures are called hybrid structures. Therefore, complaint structures are mostly hybrid structures. Okay? They are stiff in heave, roll and pitch. They resemble fixed structure in these degrees of freedom because they are all vertical plane. They are not allowed to float freely in the vertical plane. Whereas in the horizontal plane, they remain completely flexible. So, look at this figure again, displacement along x, along y, along z, about x, about y, about z. Okay. Having said this, we have already seen different types of complaint platforms, reiterating tension platform again because it is one of the most successful complaint platform commissioned in deep waters. So, tension platforms are positive buoyant systems. What do you mean by positive buoyancy? The buoyancy exceeds the weight. Okay. If you look at the static equation of equilibrium, which we wrote earlier, buoyancy exceeds the weight, therefore, buoyancy should be equal to weight plus something, and this value is the axial tension in the tethers. Okay. So, when buoyancy exceeds the weight, they are called positive buoyant structures. So, these structures are compliant in surge, sway and yaw motion. So, they are flexible, whereas they are very rigid in the vertical plane motion such as roll, pitch and yaw. Having said this, let us discuss about the second type of complaint platform, which is also encouragingly important, which is called tension buoyant towers. A figure which is drawn on the screen is a typical sketch of a tension buoyant tower. This is similar to that of a spar. You can notice the spar. So, it has got a deep draft cylinder. This is the immersion of the cylinder, which is about 80% of the total depth of the cylinder. Then the bottom of the cylinder is anchored to the seabed. Okay, it is anchored to the seabed using tendon. You must be realizing what is a tendon at this point of time. Tendon is nothing but an axially stretched wire or a rope, but the diameter is very high. Therefore, be very careful that they are not simulated to be a simple wire as you seen for electrical cables. They are large diameter members, that is why we call them as tendons. Okay. So, tension buoyant towers are another alternate where there is only one leg and the superstructure is fixed on that leg, and this is equivalent to what we call as a spar platform, which we discussed earlier in the previous lectures. Emerging these two, tension platform and spar, the new concept of Triceratops was developed. Then what is the Triceratops? Look at this figure. Triceratops has 3 legs, 1, 2 and 3, therefore the name tri. Okay, they have got 3 legs. These 3 legs can be either circular or elliptical. We will talk about this shape configuration later. Let us imagine that they are all circular buoyant legs. So, there are 3 legs which is supporting the deck. So, this is the deck and these are the 3 legs. We call them as buoyant legs. Okay. Now, resemble that 80% of the leg is immersed in water. So, what does it mean? This is similar to what we have a spar. Okay, similar to that. And the bottom of the leg is connected to the seabed using tethers. So, can you say this equation or behavior is similar to a TLP, whereas bottom of the leg is connected to the leg or the seabed using tethers or tendons. So, these are tendons, these are buoyant legs, this is the deck. So, now I can say Triceratops is a combination of spar and a TLP. Can I say that? It's a combination, it's an hybrid variety of spar and TLP. Now, what is the innovation in this geometry? The innovation is the ball joint. In both the previous cases, deck was made to rest on the leg directly, but here the deck is not resting on the leg, but the ball joints separate the leg from the deck. So, the deck is partially isolated from the legs. Okay, what is the advantage of this? A intensive research has been carried out on the preliminary studies of this, which is patented to IIT Madras upon me. So, let us see what is the advantage of the behavior of a Triceratops. Ball joint which is placed between the leg and the deck separates, or I can say isolates, partially the deck from the leg. So, ball joints provide rotational compliancy. So, it means when the legs rotate, deck do not rotate. When the deck rotates, leg do not rotate. It means the rotation is not transferred from the leg to the deck or vice versa. We already recollect that rotational degree of freedom about z axis, which is called yaw motion, is a flexible degree. It is one of the compliant freedom the structure has. So, the structure has a freedom to rotate about z axis. Look here, the structure has a freedom to rotate about z axis. So, when the deck rotates, it will not be transferred to the leg. When the leg rotates, it will not be transferred to the deck, because this rotation will be absorbed by these ball joints. So, now we can say ball joints provide rotational compliancy between the deck and the legs. What are the benefits of this? Wind forces acting on the deck will not affect buoyant legs. Wave force acting on the buoyant legs will not affect the deck, and deck and buoyant legs are independent in terms of rotation. If the leg rotates, buoyant leg may not rotate. If the deck rotates, buoyant leg may not rotate, and vice versa. So, they are independent. However, the heave degree of freedom, which is a stiff degree, is monolithically transferred from the leg to the deck. So, friends, the stiff characteristic or the rigid parameters of a compliant structure in terms of heave is maintained in the design. So, the heave motion of the leg will be transferred to the deck directly, whereas the rotations will not be transferred. So, that is why we say ball joints partially isolate the deck from the legs. Having said this, we now understand that Triceratops have heave, roll and pitch degrees of freedom which are stiff. They are very good for ultra deep waters. Friends, I am talking about water depth exceeding 1200 to 1500 meters. Okay. The platform maintain a relative low heave response even in rough sea conditions, and the platform can remain operational even during accidental collisions. That is very important. When the platform is subjected to any boat impact on the deck because of some accidental scenarios, the platform will never get capsized or damaged. It can sustain that kind of impact load caused by the boats or vessels. Okay. Now, let us see what is an additional advantage this platform has. This platform, apart from being used for oil and gas exploration, can also be a candidate for rocket launcher from the sea. As we discussed in the last lecture, there is a possibility of, we say, seaborne launches as Made in India concept in 2040. So, this is one of the important candidates which can be used for rocket launching from the sea. So, if you do that, what would be the consequences in the design? What we will discuss now. So, typical Triceratops is now being expanded to introduce a cantilever segment from where the rocket will be now launched. Okay, I have a rocket launching pad here, which is extended as a cantilever part of the deck with a bracket. Okay, the platform is extended for missile launch from the deck, and we all see the other activities happening on the deck like flare boom, derrick, etc., which are all conventional for an offshore platform. This is the point of the deck where it is going to be launched. Okay. Now, you further see that the buoyant legs are isolated from the deck using the ball joint, and interestingly friends, the center of gravity or the mass center of the whole structure lies here. Okay, it lies here. Now, let us look at an imagined floating structure which is placed in water at a very high water depth of about 2000 meters. 2000 meters. A very high water depth. Okay. Let us see a close view of this again. In plan, there are 3 legs. Okay. If this becomes a predominant wave and wind direction, so we name these legs as buoyant leg 1, buoyant leg 2 and buoyant leg 3 for our order. Okay. 1, 2 and 3 for our order. So, each leg has got tethers or tendons of 3. So, 1, 2 and 3 are in leg 1, 4, 5 and 6 are in leg 2, 7, 8 and 9 are on leg 3 respectively. Let us look at the elevation of this again closer. So, this is the point where the space launch of rocket going to happen from the platform. Pay attention, and this is a helipad we have, crane, drilling derrick, flare boom, living quarters, accommodation, electromechanical systems, all are common what we have seen in the superstructure of other structures of maritime systems. The one which is addition here is this part. Now, why we are recommending this particular launch from this platform? The advantage is the isolation. For example, when rocket launches from here, it leaves what we call as a thrust force. This thrust force will try to make a cantilever action on this deck, which will create a moment of the deck because of this continuity, and this will not be transferred to the leg. This will not be transferred to the leg because these ball joints will partially isolate them. However, if you start doing this rocket launch in a platform where these isolations do not happen, then this substructure will also get affected by the rocket launch system. Okay. So, these are the leg arrangements we have. Let us say for example, buoyant leg has 4 tethers, 2 has another 4 and 3 has another 4. Remember the nomenclature, 1, 2, 3, 4 are here, 5, 6, 7, 8 and so on. 1 and 3 are opposite, 2 and 4 are opposite. It is a numerical model of this platform where these legs are also intermittently connected, what we call as stiffened legs. Let us look at the rocket launching parameters which are used for this kind of system study. We can use small rocket, medium, medium large, large and very large rockets. As per the data taken from the literature, these rockets impose a thrust of this value back when they are fired from the platform. They also induce something called peak thrust moment, which is indicated here, okay, which will create an impulse load of so much of each type of rockets. And each rocket has got a concentrated mass of the fuel when it is going to be fired from the platform. So, this data helps us to understand or to make the model of this for further dynamic analysis. And in the present of this condition of rocket launching, the platform also experiences wave forces and wind forces. We will talk about the spectrum of wave and wind later part in this course. Let us believe that we know how wind and wave are quantified as a load on these kind of maritime structures. We will discuss this in detail in the later part of this course. So, now I have a combination of rocket mass causing impulse, causing thrust moment and the axial thrust on the deck in addition to waves and wind. Okay? Let us analyze this platform quickly and see what happens. Pay attention to these responses. The responses are topside and buoyant leg separately. So, if you look at the grey line, these are all responses of the deck, whereas these are responses of the leg. Now, one can see the response of the leg is higher than the deck in heave degree, because the heave degree is imposing thrust on the platform and the thrust is transferred to the deck, but the deck absorbs it because of the ball joints. However, this imposes hydrodynamic effect on the water body below and therefore buoyant legs are excited, but deck is not excited. Let us look at the rotational degree of freedom pitch. The red one indicates the pitch motion of the leg, whereas the grey one indicates pitch motion of the deck. This is a leg and this is the deck. So, because of the impulse moment caused by the rocket launcher, deck is subjected to high moments, because pitch is a moment degree of freedom, rotational degree of freedom. So, high rotation, whereas the legs are not. So, ball joint is now experiencing different kinds of behavioral phenomena during the rocket launch. So, the isolation helps to filter this rotational transfer from the substructure to the superstructure, causing response reduction from the leg to the deck or vice versa. Let us now talk about the response of topside with and without rocket launch. Let us say the orange one, what you see here is when the rocket is launched. The blue one, what you see here is without the rocket launch. Without the rocket launch, the steady state response is having less intensity, but the rocket launch increases the impulse because of the rocket being launched from the deck. So, rocket launch induces transient effect on the system, both in heave degree and pitch degree of freedom. Having said this, let us look at the power spectral density function on different degrees of freedom. Let us look at the power spectral density function in surge, heave and pitch. We know surge is a flexible degree of freedom. So, you have large amplitudes of surge response in the deck as well as in the legs, whereas the surge response on the deck is higher. Blue one is the deck, okay? Blue one is the deck, blue one is the deck, blue one is the deck. So, surge response of the deck is higher compared to the legs. These are all legs. So, the ball joint isolates, filters the response of the complaint degree from the deck to the legs. Furthermore, look at the peak wave frequency. Peak wave frequency is here, whereas the peak amplitude of such frequency is here. So, the design isolates the peak wave frequency from the surge frequency. It means system does not resonate in the wave condition. This is in surge degree. Let us look at this in heave degree. In the heave degree, one can again see the response in the deck is higher, the legs are lesser. So, there is a filter. Similarly, in pitch degree of freedom, the response in the legs are higher, whereas in the deck is minimum. So, there is a filter happening in different degrees of freedom because of response control offered by the ball joints. Having said this, let us now also talk about the variation in relative deck response due to different rockets. So, we are imposing the study on different types of rockets which we saw in the last table. So, one can see that very large rockets of high mass, high impulse causes very high response on the platform, whereas the platform is suitable for medium and small rockets. Okay. So, you cannot plan to have a rocket launcher of a very high tonnage on these kind of platforms. Then in that case, we should also be interested to understand the stability analysis of this platform. What happens if one of the legs gets disconnected by accident? So, I remove one of the legs, one of the tendons, and understand tether failure. We call this study as postulated tether failure. Postulation is an imaginary failure, right. So, we call this as postulated failure. So, when you do a postulated failure, one can see when there is no postulated failure, the platform experiences very minimum response in heave. But when one leg fails, it is marginal. When two legs fail sequentially, it is higher, but the platform does not exhibit larger difference. See that. Initially it is 26.2, it has moved to 26.8. There is a marginal difference. So, the platform being positive buoyant system, even when the legs fail, they sustain the failure. Okay, that is important. We can also see how does it behave in leg 2 alone under this situation. Let us look at the pitch degree of freedom in leg 2. When no postulated failure occurs, the response is very simple. When one tether fails, it is here. When two theta fails, it is here, but it is moving from the mean positive and negative, okay, by the same amount. So, there is a balance in terms of successive sequential failure happening in pitched motion because of postulated tendon failure, which assembles and confirms that the platform is stable. Friends, let us look at the phase velocity plots, which plots heave velocity versus heave displacement in a system. So, when there is no failure, it is an elliptical trajectory. When one postulated failure happens, it is again elliptical trajectory, but the mean shifts. Okay. When 2 and higher failure happens, again elliptical, but the mean shifts. Friends, in phase velocity plots, elliptical trajectories confirm that the system is stable. For large displacements, the velocity is very minimum because this displacement is velocity. For large displacements, velocity is minimum, and elliptical trajectory confirms that it is stable in heave motion, okay, and in pitch motion also. This is pitch and this is heave. So, friends, even when the legs fail one by one sequentially, the system does not lose its stability when the rocket is being launched. Stability charts are also prepared to ascertain this using Matthews stability. Matthews stability will be discussed in another course, dynamic analysis, later. You must be aware of this particular methodology of assessing dynamic stability using Matthews stability charts. So, Matthews stability charts also confirm that the system remains stable by plotting two variables delta and q, which are called Matthews parameters of stability indicators. So, friends, we now understand that Triceratops being a new generation platform is good because it induces partial isolation between the substructure and superstructure. Though the response is significant in complaint degrees of freedom, but still it is controllable. It can be used as an additional task of rocket launch in seaborne condition. We say this as a smart design of maritime structure which is highly stable even during rocket launch. To believe this and to understand how this is constructed, now I will move on to show you a video. Friends, please watch this video. The left top shows an animation which has been done in the software. And the right one is an experimental value which is shown. You can see the legs are all rotating, but the deck is not rotating at all. Not coming? The legs are rotating, but the deck is not rotating at all. So, the ball joints provided here between the leg and the deck are isolated. Okay? And the left hand top shows you an animation of this picture, which is a Triceratops commissioned in deep water conditions. Let us see how this is installed, the construction sequence of a Triceratops. So, there are 9 steps of installation. See one by one. The buoyant legs are dragged to the site, then they are appended, they are ballasted, and they are connected to the teethers, and then the foundation by suction bucket. You also vary the ballast to improve the weight. Once they are ascertained, initial tension is imposed, then the ball joint is placed on the top of the leg. 3 such legs are placed in position, then the deck is brought on a barge and placed over these ball joints, and the construction is now completed. So, the construction sequence of a Triceratops is very interesting and simple compared to what we have in complaint structures. So, friends, in this lecture we discussed about a new generation platform which is Triceratops. Friends, Triceratops remained as a concept in 1997 onwards, but IIT Madras and IIT Gandhinagar are conceiving this idea to make it into reality, to commission these platforms for different maritime applications in the near future. So, this is a very stiff degree of freedom in heave. The platform remains safe and stable even for additional applications such as marine launch of rockets of small size or medium size, not a bigger one, but smaller medium size. This is essentially for data acquisition and exploration purposes, not for any defense purposes. Okay? So, this lecture will help you to understand. I hope you have followed the lecture. Please post your questions in email to the instructors in SwayamPrabha portal, and try to follow these lectures by repeated references as mentioned in the initial page of this particular portal, and I urge you to understand them, learn them, and also apply these concepts in reality by exploring these designs in different geometric forms as you go ahead in maritime engineering innovations. Thank you very much. Namaste.